السلام عليكم ورحمة الله وبركاته. Yeah, let's move on. Remember, today we will have our major 2 exams. Okay. I've already informed you up to which lecture it is going to cover. Okay. Before we start the Eulers equation today, I would just like to highlight some few things with respect to acceleration. Okay. I'm describing the acceleration field. Yeah. So if an acceleration is, let me go to the presentation mode so that it will be bigger. Time rate of change of velocity, or rate of change of velocity with time. Okay. And then there are 2 main components of acceleration when it is traveling along a curve, okay, or curvilinear path. Okay. It will have 2 components, tangential and normal acceleration. Just like velocity, we discussed this with velocity as well. The tangential acceleration is directed along the tangent of the path or streamline. In this case, if we're considering free particle, the normal acceleration is perpendicular to the tangential one, which is at 90 degrees. For velocity, same thing. You have velocity, the tangential velocity, and normal velocity. En and Et are unit vectors directed along the normal and tangential components, respectively, just to give direction to the vector velocity. And we have the same thing for acceleration. Some text we use U, UN, and UT to denote the unit vectors. Okay. We all know unit vectors from statics, just giving direction to the force vector. Okay. And we derived the acceleration to be this. Okay. The tangential one. And in dynamics, you should be taking dynamics now. Okay. In dynamics, that is ME201. You will derive this equation here. Okay. This is the tangential acceleration unit vector, and this is the normal acceleration unit vector. And this is AN, the magnitude of the normal acceleration, which is v squared over r, and this is AT, magnitude of the tangential acceleration, which is consisting of 2 components, del v del t plus v del v del s. Okay. Plus v del v del s. Del v del t is the rate of change of velocity with time, which we discussed about this. It gives the local acceleration, isn't it? No, this is the convective, or in this case, advective acceleration. Sorry, the local is this one, because local is having to do with the space. Okay, so this is the local acceleration component, and this is the advective acceleration or convective acceleration. Okay, as the case may be. Okay, because it is advecting with time. Okay, and this is local because it is at a particular point. It is considered within space. Okay, displacement, certain distance. Okay, within some space interval. Okay, this is having time as the parameter, is variable, and this for steady flow we say this time will be 0 for steady flow because it doesn't change, the velocity does not change with time. Okay, and for steady flow, I already explained what steady flow is, but I still want to emphasize one thing. Okay, You see, we discussed about nozzle. Okay, I will go back to the nozzle and explain again. So this is the local acceleration, like I mentioned, and this is the convective acceleration or advective acceleration, as the case may be. And this is the tangential component of the acceleration, and this is the normal component of the acceleration. Okay. We just want to emphasize on the nozzle. Yes, you see, the velocity here at the inlet, Vi, is less than the velocity at the outlet. So Vi is less than Vo, meaning the velocity changes. The value of the velocity here is different from the value of the velocity here. But steady flow, you are fixing your position, meaning at a particular section, and observing the flow across that section. So if you come to this section, okay, the velocity here, which is V naught, does not change with time. It remains the same value. Although it doesn't mean that the velocity throughout the space is the same. No, if it is the same throughout the space, that is when it is uniform flow. Okay, for steady flow, you fix your position and observe the velocity. When you fix your position here and observe the velocity at the inlet, it is constant, Vi. It does not change with time. Okay, but it doesn't mean that the velocity throughout every space is the same. No. So that's why steady flow, it means it is steady, meaning the given value at that point in time, at that space, at that location, does not change, does not vary with time. So this is very important. You need to understand really the difference, the exact definition of a steady flow and uniform flow. And you remember for the uniform flow, well, we used the advancing front, the fully developed flow. I want to check the figure that there is a figure. Yeah, this figure. You see at the inlet here, I analyzed this before, but just to, again explain, because to understand exactly uniform flow, you see, in this case at the inlet, the flow velocity, for example, the fully developed pipe flow velocity profile is certainly not uniform for calculation purposes. Okay, sometimes approximate, okay, to make it uniform. But at the inlet, it's common to approximate flow in ducts and pipes, and at inlets and outlets as uniform. At the inlet, the velocity profile here, it means at every point here, the velocity is having the same value. Let's say Vi. Okay, so at this portion, the velocity is uniform in this portion. Okay, when you go to the second portion, you can see the arrow, because the magnitude of the velocity is negated by the length of the arrow. The length of the arrow, the velocity vector here is less than the length of the velocity vector here. So the velocity here is different from the velocity here. Okay, and it's somehow uniform here, and then it decreases because of the boundaries. Okay, because of the shear force, the viscous force acting at the boundaries. So here it is non-uniform, and then here is also non-uniform, definitely, of course, as it moves on, because you can see the velocity varies over the profile, it changes. But here is the same. Okay. Okay. And now talking about acceleration again, the velocity here at this point is different. When you look at the center point, the center line, streamline, okay, which is this one now, okay, is the velocity changing? At this point, the velocity here is less than the velocity here. It increases again, it increases. You can see the velocity increasing. So if the velocity changes, you have acceleration. So particle traveling along the center line streamline is accelerating because the velocity is what? Changing with time. You can see it. it is changing with distance, it is changing with time. So it is accelerating. But now, when you look at this section, when you come at this section, when the flow is fully developed, it means that the velocity is no longer changing with the flow along the z direction. It only changes along the flow vertically, along the radial axis. Okay, so this developed profile, fully developed velocity profile, will be maintained throughout the remaining sections. Okay, so at this point, the velocity remains the same at every section. This velocity at this section, it doesn't change. Okay, even though here you may have also steady flow, it may be steady, but it is definitely non-uniform, because it is steady, because the velocity at a given point do not change with time, but it changes with distance. That is, when you move from here to here, the velocity of this point is different from the velocity of this point. So it changes with distance. That is non-uniform. But with time, at this point, if the velocity remains the same, then it is steady. It is steady velocity. It is steady flow. You have a steady flow at that point. Okay. Now, still on the acceleration, because now on the Euler's equation we will talk about acceleration. So that's why I'm still like emphasizing about some important points pertaining to this. Okay. And so yes, so this is an example. The velocity along a path line is given as this: v equal s squared t to the power of 0.5. So you see the velocity varies with both space and time. Okay, where s is in meters and t is in seconds. And the radius of curvature is 0.4 meters. Evaluate the acceleration. The radius of curvature is for the normal acceleration, which is v squared. Let me write it here. It's not over there. V squared over r. So r is the radius of curvature. This is for the normal acceleration, which is directed towards the center of curvature of the curve. Okay. So evaluate the acceleration along the normal, tangential, to the path at s equal 1.5 and t equal 0.5 seconds. Okay, so we want to evaluate the acceleration along the normal and tangential. Okay, so what is the normal acceleration? Which is this? So it's very simple. For the normal acceleration, v squared over r. Okay, so v is given as s squared t of this over r. R is given as 0.5. Okay, so we now evaluate this at what? T equal 0.5 and s equal 1.5. Simple. So we just simply substitute s as 1.5 here. T is 0.5 to the power of 0.5, then divided by 0.4. Sorry, this is 0.4, which is the radius of curvature. And whatever we get here will be the normal acceleration. But for the tangential acceleration, which is v del s plus del v del t. Okay, so for this, we need to evaluate, to differentiate this with respect to time, differentiate it with respect to s, okay, and then substitute in here. When we differentiate, we also, so like del v del s is simply differentiation 2s t to the power of 0.5. Okay, you do the same thing, del v del t. Okay, and then you substitute here and evaluate the tangential acceleration at t equal 0.5 and s equal 1.5. Very simple. Okay. So now, again, before we start the Euler's equation, I would like to draw our attention back to something fundamental in statics, okay, which is the Newton's laws of motion. This you did it also. It was treated in physics 101, definitely. Okay, Newton's laws of motion, they form the fundamentals. I mean, the main foundation of most of the courses in mechanical engineering and civil engineering. Okay, so you need to understand these laws very well, and at no point in time should you fail to be able to explain each of these laws. They are one of those things that I always tell my students that you are not allowed to like say, no, I forgot. Okay, you cannot forget Newton's laws of motion. As long as you are a civil engineer, you cannot. You can get your BS, MS, PhD. When we were interviewing last week, almost every interview I asked the candidates to state either Newton's first law, second law, or third law and explain. That is those with PhD applying for professorial position. You can imagine that. And they took it last when they were at your age, I mean, at your level, at undergrad. But you cannot forget these laws. They form the rock solid foundation of engineering disciplines, most of the engineering analysis, computations, and what have you. Okay, and also in statics, it was briefly reviewed in chapter 1. So I will briefly review the Newton's laws of motion and then move on to the Euler's equation. Because the Euler's equation is based on the Newton's second law of motion. Okay? All right, the first law is simply telling us about an object that is at rest and is acted upon by forces, okay? Unbalanced force in particular. When an object is acted upon by a balanced force, it remains in state of rest. Or if it is moving with uniform velocity, it remains in that state if the forces are balanced. But if the forces are balanced, then the second law explains. But what do we mean by balanced forces? Let's say this is someone. Now this is your friend pulling you to this side. This is another friend of yours pulling you to this side. This one applies 10 Newton force to pull you. This one applies 10 Newton force. So this person at the center will remain in his current state of equilibrium. He will not move to the positive x direction, neither to the negative x direction, because the forces applied are balanced. And balanced in the sense that this algebraic sum of the forces is equal to 0. That is what we express as summation F to be 0. The vector sum of all the forces equals 0. This is in the x direction. So this is minus 10 plus 10, 0. Okay, so we say the forces are balanced. But if he chooses to increase the force here to, let's say, 100, definitely the forces are not balanced. And there is a resultant force now. Okay, resultant force in the x direction, which is now 100 minus 10, which is 90 Newton. Okay, so in this case, the person will have to move in the direction of the applied force. And that is the Newton's second law of motion, what it is saying. That when an unbalanced force is acting on an object, the object accelerates. By accelerating, meaning it will have velocity, and that velocity will change with time. Okay, it accelerates. Okay, and the acceleration is proportional to the applied force and takes place in the direction of the applied force. And that is when we say the applied force is proportional to the acceleration. Okay, and when we remove the proportionality sign, we introduce a constant, which is the mass of the object. Okay, this is the mass. And that tells us about inertia. Okay, mass constitutes the inertia, the tendency of the body to move if it is at rest, the reluctancy of the body to move if it is at rest, or the reluctancy of the body to stop if it is in motion. Okay, but the sum of all the forces acting should be equal to MA. Here I just gave example of one force, but you can have many forces acting. So algebraic sum of all the vector sum of the forces should be equal to MA. Force is a vector, acceleration is a vector. So you can see F equal MA. So the acceleration acts in the same direction as the force. What about if I have F equal M minus MA? It means it is acting in opposite direction, and that is for deceleration. When you have the velocity is increasing with time, we say it accelerates. When the velocity is reducing with time, it decelerates. We say deceleration. Deceleration. It decelerates. Okay, opposite of accelerate. So here it accelerates. If acceleration is in this direction, then deceleration, which is negative of acceleration, is going to be in the opposite direction. okay, is going to be in the opposite direction of acceleration. We will also talk about this when explaining the Euler's law. So what we are saying in the second law of motion is that the sum of all the forces acting on a fluid particle is equal to m times its acceleration. Or we can convert it, because the acceleration is dv dt. Okay, and mass times velocity, we call it momentum. This you did in physics, momentum. Okay, so we can now say that the algebraic sum of all the forces acting on a body is equal to the rate of change of momentum, because this is rate of change of momentum. And for fluid particle, what are these forces? The forces are basically the pressure force and the gravitational force, which is as a result of the weight of the fluid. These are the two forces acting, okay? So these forces, when we sum them up, they should be equal to ma, or the rate of change of momentum. Okay, and this forms the basis of the Euler's equation. The Newton's third law is simply saying that action and reaction are equal and opposite. That when you have a body acting on another body, okay, so this exerts a force F, and this one exerts equal but opposite force F. When you place an object on a table, it exerts its weight on the table. The table exerts equal but opposite reaction on the body. Okay, equal but opposite reaction on the body. This you must have done under friction and analyze the reaction, and all that. Sometimes the action may be greater than the reaction. If this happens, then it means there will be net movement downward. Okay, and this is exactly what happens for buoyant force. Buoyant force. Remember that ship, that ship, different position. In this case, we said that the weight is equal to the buoyant force, B, isn't it? When it is completely immersed, okay, we still have the buoyant force reaching maximum value, but it is still equal to the weight. It is still equal to the weight of the ship. But when you added the weight of the ship, that it sinks to the bottom, then in this case, the weight W is greater than the buoyant force. But you still have the buoyant force, but the weight is greater than the buoyant force in this case. So the buoyant force is less than the weight. So that's why it pushed the buoyant force down. Okay, but in this case, buoyant force is equal to the weight. In this case, the buoyant force is also equal to the weight. But in this case, the weight is greater than the buoyant force. Okay, so this is the consequence of Newton's third law of motion. Okay, these three laws, like I said, you have to understand them. You cannot forget them. All derivations in mechanics, anything mechanics, is based on this. Newton's laws of motion are the backbone of the subject mechanics. Anything mechanics. You can have mechanics, solid mechanics, structural mechanics, anything mechanics, or anything statics and dynamics, fluid dynamics, gas dynamics, and all that. It forms the backbone. Okay, now let's move to the Euler's equation. Now, pressure variation. You remember that we said for hydrostatic condition, okay, so the sum of the forces acting along a particular direction is equal to 0, according to for equilibrium. Okay, this we discussed before when we have static fluid, isn't it? When we have static fluid, okay, where we say this is the piezometric pressure, isn't it? Or piezometric head, the piezometric pressure head, okay, or piezometric head, okay. This value is the same for all points, okay, because it simply implies that the pressure head, which is due to the weight of liquid acting above, okay, plus the elevation head, which is due to elevation of the particle above a given datum, is constant. So we proved this before, that for every point you consider, the piezometric head or the piezometric pressure is constant for static fluid. Okay, and this we developed from this one, okay, from the Newton's second law of motion, that the sum of forces acting is equal to 0, and we describe the forces in this case as pressure force and the gravitational potential force. Okay, this we did derived in previous slides. Okay, I'm just like taking your mind back. But now, this is for static condition, okay, in which the fluid is contained in is enclosed in a container, not moving. What about moving flow condition? Now the Euler's equation will now come into play. Rather than having the sum of the forces acting on the fluid element to be zero, like in this case, because in this case it is not moving, it is in equilibrium. The fluid particles are all in equilibrium. What about if it is flowing in open channel or in pipe, okay, in pipe flow? Then the sum of forces is not equal to zero. It implies that the fluid particles are accelerating, okay? And once they are accelerating, then the sum of the forces in any given direction should not be equal to zero, but should be equal to ma, okay? The L is just selected direction. It can be x, y, z, okay? So which we can write in vector form, summation f equal ma, representing both the force and acceleration as vectors. Okay, so in that case, it will take care of any selected direction, because here, when you expand it, you know, in 2D or 3D, forces, the sum of forces will have fx, fy, and fz, and acceleration also will have three components: ax, ay, and az. This we discussed before about the acceleration field. Okay, so this forms the basis of the derivation. So here, you know, we use the same figure as we use when deriving the hydrostatic differential equation. Okay, you remember the hydrostatic differential equation, dp dz equal minus gamma. So this is the hydrostatic differential equation. Okay, so we have the same fluid element when we're considering this direction, L direction. Okay, and you have pressure which is compressive acting at both faces. Okay, this is the cross-sectional area, and it is inclined at angle alpha. Okay, now the sum of forces acting, because it is moving, this is a moving fluid. Okay, so it's equal to ma. So we basically have the pressure force and the gravity force, okay, in form of weight. Okay, it's equal to ma. So this is similar to what we did. This is the mass, you know, because this is the volume. Density is mass over volume. Okay, and the pressure force, you know, we use the vector form. Okay, this minus this. This is the positive in the L direction. That is the positive. Okay, and the gravity force is simply the weight of the element. Okay, which is the component of the weight along the L direction. And then we now substitute and simplify and equate it to ma. Okay, this is a and this is al, the acceleration in that direction. Okay, and now when we take the limit of delta L approaching to zero, so it means we are reducing the particle to an infinitesimal size. So we change it from delta P by delta L to del P del L, okay? And then this is equal to rho AL, okay? And then when you look at this, P plus gamma Z, this is exactly the hydrostatic, this is the piezometric pressure. If you remember from here, this is piezometric head, and then when we multiply by this gamma, we will have P1 plus gamma Z1 to be equal to P2 plus gamma Z2, okay? And this we call PZ, okay, which is the piezometric pressure, okay? The piezometric pressure. P plus gamma Z, you know, this is the piezometric pressure, okay? So in this case, we are now saying, so this is the scalar form of the Euler's equation, okay? Because this equation is true in any scalar direction. L is simply any given direction. It can be x, y, or z. And we can write its equivalent form to take care of all the directions using gradient. You remember when discussing the acceleration field, we discussed gradient, okay? And gradient is simply I del gradient vector. It is a vector, okay? It is simply del by del x I plus del by del y a plus k del by del z. Okay, so it takes care of all the directions x, y, and z. Okay, and it is a vector. Okay, so when you now introduce this, so this is simply del p, we call it nabla, okay, nabla, okay, or grad, or or del, okay. So del p is equal to rho a, but this is a vector, that's why it is bold, and the acceleration here is a vector, but density is not a vector quantity. This we already know. Okay, so this is a simplified form of this, and this is the Euler's equation. And what is this telling us? You can see this is minus del p z is equal to rho a. We are now giving direction to the, it's more or less giving us the pressure field. Okay, Euler's equation is more or less giving us the pressure field. The pressure field and the direction of the gradient is in opposite direction to the acceleration. You can see because of this minus here. It means the pressure gradient and the acceleration are in opposite direction. Meaning if the acceleration is this way, then the pressure gradient LP will be in the opposite. That is the minus sign. Okay, so we are going to look at the interpretation of this. Okay, is the solution of the fluid particle. Yeah, so this is del gradient or del operator. Okay? Gradient or del operator. This is its definition. Now, this is the Euler's equation. Okay, minus del, which we can just simplify as LPZ is equal to rho A. Okay, using the gradient operator. Okay, and it can be used to determine the pressure in flowing fluids. Okay, it can be used to determine the pressure in flowing fluids. We are going to see later exactly what is really the definition of pressure. What is this pressure? Although we discuss about pressure, you know, in solid, pressure is simply force acting over the area. Okay, if you are standing, I mean, you exert your weight, which is the force acting on a given area. So when you divide, you find the pressure. Okay, that is for solids. For liquids or gases per se, fluids in general, what is pressure? Water pressure. What is this? We are going to see later. It is simply a measure of the potential energy contained in a fluid per unit volume. Okay, it is simply the potential energy per unit volume. Okay, the potential energy contained in a flowing fluid or in a fluid at rest per unit volume, because pressure is Newton per meter square. Okay, Newton over meter square is equal to Newton. You can multiply by m square. You can, yeah. So I haven't done anything, and this force times distance is energy or work. Okay, which is usually in this case will be potential energy. Okay, and m squared times m is m cubed, which is the volume. So it usually gives us potential energy contained in a flowing fluid or static fluid per unit volume. We are going to explain later when discussing the Bernoulli's equation why do we define it using potential energy, because force times distance, it can be any other energy, kinetic energy and whatever. Okay, and that is simply because the pressure in fluid equal to rho gh, and the potential energy is equal to mgh. So if you substitute the potential energy here, you will see that you will arrive at this. It is because of this relationship. The static pressure is rho gh, and this is the potential energy. So when you compare them, you come to the realization that pressure is actually a measure of the amount of potential energy contained in a fluid element per unit volume, or contained within a given control volume per unit volume. Okay? Now, on the physical interpretation of Euler's equation, I've already started giving the explanation of the the interpretation. Euler's equation shows that the pressure gradient is collinear with the acceleration vector and in opposite direction. Okay, it's collinear. They're the same, just like you have in the Newton's laws of motion summation F, we call ma. Okay, so F and A are collinear. But in this case, because this is positive, they lie in the same direction. But in this case, because it is negative, they lie in opposite direction. Okay, but they lie on the same line. This is the gradient of the piezometric pressure field. Okay, this is density, which is mass over volume, and this is the acceleration of the particle. Okay? Thus, using knowledge of acceleration, one can make inferences about the pressure variation. Meaning, if you have knowledge of the acceleration, you can make inferences about the variation of the pressure field. Okay, and this we will look. And still on case one, we will look at different cases for the application of the Euler's equation. So we'll start with case one, which is the pressure variation due to changing speed of a particle. What happens if a particle is changing its speed? Definitely it is accelerating, but let's analyze the problem. When a fluid particle is speeding up or slowing down, when it is speeding up, it means the velocity is increasing with time, so it is accelerating. When it is slowing down, it means the velocity is reducing with time. Just like you traveling at 120 kilometers per hour, and then you enter a region whereby the maximum speed limit is 100. So you have to slow down, isn't it? So the speed will reduce from 120 to 100. Okay, so you are accelerating in the negative way, which we call deceleration or retardation. Okay, so when you have a fluid particle speeding up or slowing down as it moves along a streamline, considering streamline, that is, the line in which the velocity vector is always tangent to that line. And normally, as we always mention for steady flow, streamline corresponds to the path line. That is the path traversed by individual fluid particles, okay, at a given point. So, a given at a given point. Pressure will vary in a direction tangent to the streamline, okay? Pressure will vary tangent to the streamline. You have flow in this direction. We are considering this streamline, which we call the stagnation streamline, okay? Because it is moving towards this sphere, okay? This figure shows flow over a sphere. The blue object is a fluid element moving along the stagnation streamline. We analyze this, okay? When it is moving towards this streamline, when it hits the sphere, it is going to come to rest, okay? While others, you can have like attached flow, and then others can be even undisturbed, okay? You can have areas where you have no viscous effect or low viscous effect. But the stagnation streamline is the one that will hit the sphere at its center, okay, and thereby coming to rest. Okay, the fluid particles along the stagnation streamline will come to rest after reaching the point where it will touch the sphere. That is this point. Okay, so because this particle is slowing down, the acceleration vector must be tangent to the path and acting to the left. This particle, as it is moving, it is slowing down because it is finally coming to rest here. So it is slowing down. If it is slowing down, it is decelerating. Okay? Negative acceleration. And negative acceleration will be in the opposite direction, isn't it? If it is accelerating, then it will be this one. That is, if it is speeding up. But if it is slowing down, then it will be in the opposite direction. That is, the direction of the acceleration will be deceleration, which is opposite to acceleration. Okay, so it is slowing down. That's why the direction is this way. Okay, so if this is the direction of the acceleration, then the direction of the pressure field or the gradient of the pressure will be in the opposite. Therefore, in this case, the pressure must be increasing to the right. So the pressure will be increasing. While if it is the case, if it is accelerating, then the pressure will be reducing. Okay, we are going to look at that case also. So this is along, a rectilinear point or a rectilinear streamline. Okay, straight streamline. Okay, which the acceleration in this case is purely tangential action. We have no normal acceleration in this case, because the radius of curvature in this case for straight line is infinity. Okay, and the normal acceleration, remember, is v squared over r. So if this is infinity, then the normal acceleration is equal to 0. Okay, for straight line. What about if it is curved? For curvilinear path, we'll examine that also. So, for example, this figure shows a fluid particle moving along its stagnation line. Because the particle is slowing down, the acceleration vector points to the left. This I explained. Therefore, the pressure gradient must point right, okay, because of the negative sign, because of the fact that minus del P Z is equal to rho A, this minus sign. So this and this must have opposite direction. Thus, the pressure is increasing along the streamline, and the direction of increasing pressure is to the right. Okay, this is the direction of increasing pressure. So the summary here is when a particle is changing speed, pressure will vary in a direction that is tangent to the streamline. That is the summary. So yeah, it is pressure will vary in a direction that is tangent to the streamline. The pressure will increase in the direction of flow if the particle is decelerating, if it is slowing down, and it will decrease in the direction of flow if the particle is accelerating, meaning if it is speeding up. Okay. Now, case 2, pressure variation normal to rectilinear streamlines. Okay, pressure variation normal to rectilinear streamlines. Here we look at just one streamline, in this case, just one single. Okay. Now, what about in a flow when you have many streamlines? Okay, let's say uniform flow, for instance, because that's when the streamlines are parallel, only for uniform flow. Okay, you remember, for uniform flow, that's when you have the streamlines to be rectilinear and parallel. Okay, they have to be rectilinear and parallel. But for steady flow, they can be straight but not parallel for steady flow. But for uniform flow, they have to be straight and parallel. Okay, for uniform flow. It's very important. So when streamlines are straight and parallel, then piezometric pressure will be constant. When they're straight and parallel, then piezometric pressure will be constant along a line that is normal to the streamlines. Okay. We already examined that when it is straight, what happens? Okay, the variation along the streamline. Now, what about normal to the streamline? Normal to the streamline, the piezometric pressure will be constant along a line that is normal to the streamlines. But it is not constant along the streamline, that is tangential to the streamline. This we explained in case 1. Tangential to the streamline, the piezometric pressure can increase in the direction of flow if the particle is decelerating, slowing down, or it can decrease in the direction of flow if the particle is accelerating. Now we are taking normal to the streamline, perpendicular to the streamline. What is the pressure variation? So in this case, the pressure variation will be constant. The piezometric pressure variation will be constant along a line that is normal to the streamline. This is normal, which is at 90 degrees to the streamline. So the piezometric pressure along every point here is the same. It remains constant. Okay. So here, let's look at the points. We look at this point. Okay, recognize that the normal component of acceleration for this particle must be 0. You know, the most important thing, we are still playing with this rho pz called A, isn't it? Okay, so we are considering the normal component. So here is going to be n. Okay, n. And in this case, is what? We say it's equal to 0 for linear streamline, isn't it? Because the radius of curvature is infinity. So that makes delta p z to be equal to 0. When it is 0, it means it is constant. Okay, which implies that p plus gamma z is equal to constant, because 0 is also a number, so it's a constant. Okay? And this is the hydrostatic condition. You know, we use this to derive the hydrostatic pressure condition, the hydrostatic equation. for the hydrostatic differential equation, okay, in which we said when you have static fluid, okay, the piezometric pressure at all points is the same. So when you take a section, the piezometric pressure on this is constant. The same thing here, okay, when it is normal, okay, the piezometric pressure remains the same, okay, so this becomes zero. So here, recognize that the normal component of acceleration for this particle must be zero. And we explain why it is zero, because it is horizontal. Oh, and the particle, my time is up. Tomorrow we will continue from here, okay? And our major today is going to be very simple, okay? As usual, you just understand the examples I provided in the class, my explanations, the quizzes you took, which you all have the key solution, and the homework, which also you all have the key solution to the homework. So once you understand this very, very well, I tell you, you will get 100%. And definitely the time provided, 1 hour, will be more than enough. Okay, so get prepared. See you at 12 o'clock. Any question? So today I had 12 participants. Okay, so 3 guys are missing today. Class. Okay, someone is asking for quiz for the 4 questions for the major. Yes, yes, just 4 questions. Okay, just 4 questions. All right. If you don't have any question, see you at 12, and then wish you all the best. There will be questions. Oh, definitely, I ask a lot of conceptual questions, so there could be. I mean, just like my class, you have numerical problems, and you have a lot of maybe like some conceptual problems in which it's not that you will be writing to fill a page with English, with theory. No, some simple things to just test your understanding of some concepts. Simple. Okay. All right. See you at 12.